All right, so let me give you a refresher here. So example, find each indefinite integral. I want to find the integral of x cubed divided by the cube root of 1 plus x to the 4th dx. Oh my gosh. How to do this? All right, so first thing to observe is this is a lot more complicated than any integral we've done in like chapter 4.1 or anything like that. So when your integral is more complicated like this and you can't do any algebra, you want to look for an inside and outside and then the derivative of the inside. Right? If you can break this into an inside and outside and then the derivative of the inside, you can use U substitution. So do you see that kind of pattern in here?
4x cubed to 4x cubed is something.
So if you, x cubed is the derivative of x to the 4th almost, right? So if you make this guy your inside, and you let the cube root be your outside, then that'll take care of all of this, and then the derivative of your inside is sitting up here. So you can, or approximately, I mean not quite, we're going to have to fix it up, but it's pretty close. So to do this, we would use U substitution with U equal to the inside function. So then du dx, the derivative of u, is 4x cubed, right? Usual derivative. And then we've been solving for du, so du is 4x cubed dx. So the way U substitution works, let me rewrite this integral because it's got a bunch of slop. A bunch of garbage in it. The way U substitution works is you need to replace each one of these x's with either a u or a du, somehow. This guy's pretty, the 1 plus x to the 4th is already done, right? That's u. This x cubed dx is going to contribute to du. Right, I need to get that 4 in there. Right, in order to use du, in order to put du in here, there has to be a 4 in front. So I put a 4 here and a 1/4 outside, or replace it with a 4th du. So there's a couple different ways to deal with that constant. One way to do it is to put the 4 in on the top of the integral, so you have exactly du up here. But you can't just put the 4 in without balancing it out. So what does my integral become here? 1/4 integral of du over cube root u. Right, so on top I have du all together. On bottom I have cube root u. But I know to integrate cube root of u, or 1 over cube root of u, I'm going to have to bring it up. Right, so cube root of u becomes u to the negative 1/3. Then you do your power rule, add 1 to the power. So negative 1/3 plus 1, 2/3 over 2/3. Kind of ugly. This 2/3 can flip up as 3/2. So 3/2 times 1/4 will be 3/8. u to the 2/3 plus c, or 3/8. Is this my final answer? Circle that. No, what do I need to do? Get back to x's. If you start in x's, you got to end in x's. So I don't want a u in my final answer if I start with x's. So instead of putting u to the 2/3, I'm going to put 1 plus x to the 4th to the 2/3. So, what do you think about that? Easy, hard? Who knows yet? Nothing. Absolutely, you think nothing.
No.
You think blank. It's okay. Okay. I wish I could think blank. Probably Buddhist monks were jealous of you guys. They strive their whole lives to be able to just think blank. So, I haven't done any trig functions for you yet. I think we need to do some trig functions. That sounds good. All right. We'll start with the baby. If you were clever enough, you could probably do this without u substitution, but let's go ahead and do it all out in gory detail so you can see it. What's your inside and outside function?
Pi x is inside.
Pi x is inside. So to do this integral, you're going to let u equal pi x. So that makes du dx, the derivative of u, just pi. Or du equals pi dx. So when I start doing my substitution, I have u, right? This guy's u, sine of u. But for my dx, I'm going to need to put a pi in front to make it du. So I'll put a pi over here, and what do I have to put on the outside?
Pi
The reciprocal, 1 over pi, I have to balance it out. So then my integral is going to become sine of u, and then the pi dx is going to be du. Right, pi dx is du. So I'll get 1 over pi, integral of sine u du. There's u. Oh, now I have to do the integral of sine. Okay. What's the integral of sine? Negative cosine. It can't just be regular cosine because the derivative of cosine is negative sine. So it's got to pick up a negative sign. So when you do this integral, you'll leave the constant out front, 1 over pi, but then it'll become negative cos u. So negative 1 over pi. Again, you don't want to leave your answer in u's if you start in x's. So I'll have to put my u back in, so it'll become cos pi x. So how can you do the integral of sine pi x without really using u substitution? What's the integral of sine x, just regular sine x? Negative cos. So sine pi x will become cos pi x, but where does this 1 over pi come from?
The inside function.
The chain rule. It's the reverse chain rule. When you do the derivative of this, the pi will pop out and cancel. If you do the integral, the pi comes out as division. So when it's just a constant times x, you can do the integration without all the formality of u substitution. I mean, most people can. But if you want to use u substitution, go for it. Go nuts. See? X. So I'm going to do the integral of x secant x squared tangent x squared. So what do I want to make u?
Secant x squared tan x squared.
So if I made u equal to secant x squared tan x squared, then my derivative du dx would be what?
1.
What's the derivative of this function?
No.
This is the derivative. This is a product rule with a chain rule inside. If you do the derivative of this, you would have to take the derivative of secant, which is secant tangent, times tangent, because that's the second function, plus, then do the derivative of this times this. That's not in there. Do you know what I mean? Like, this is not, I'm not going to get the derivative of the inside if I make secant x squared tan x squared my u. But,
If you do secant
Just
x,
x squared.
tan x, and then squared.
okay, so, remember secant x squared is different than secant x squared. These are not the same. So if it were secant squared tan squared, then I can pull the square out outside. But if the square is on the x, I can't simplify that.
Okay.
So what you want to focus on is this x here. What's x the derivative of?
X.
Basically x squared. Right? So the association here is that this is the derivative of the inside, which means if I make the inside x squared, these will match up. Derivative of x squared is basically x. So I let u equal x squared. Then du dx is 2x. So du is 2x dx. These guys are taken care of. Right? Each of these is a u. And then x dx will contribute to my du, but I need to put a 2 in front. And I need 2x dx, and I only have x dx. So I put a 2 in front and a 1/2 outside. So this becomes 1/2 the integral of the 2x and the dx contribute to the du. So all I have left is secant u, tangent u, d.
Oh.
What's the integral of secant tangent?
Secant.
Secant! Because the derivative of secant is secant tangent. So I'm going backward. The integral of secant tangent is secant. But I want u's, I want x's.
Here, replace it.
Is got a sigh of contentment. Oh, that was such a pleasing problem to do. Thank you, Josh.
But this easy ones maybe. Can I break it down?
So, I don't know, this x was really, this x squared pattern was what you had to focus in on this one. You had to just kind of push the rest out of your brain and focus on this function and its derivative to see what you should do. I'm going to go sine x cos cubed x dx. Yeah, so this one's maybe a little more clear what the inside function is. Cosine cubed x, this is the same thing as cos x cubed. So if I make my inside function cosine, that's pretty nice because the derivative of cosine is sine. So everything seems to be working out with this substitution. So if I make u cos x, du dx would be negative sine x, right? Derivative of cosine is negative sine. Then I want to solve for du. So du is negative sine x dx. So I have sine x and dx, but I don't have the negative. So I force it in there. I'm going to put a negative right here, and I balance it out with a negative out. Then I have my du right here. And then I have my u. So my integral will become, don't forget this negative, negative integral cos cubed is u cubed du, negative sine x dx. Then you're off to the races. This is your power rule. U to the 4th over 4 plus c. Plug back in your axis. Feeling confident? Okay, cool. Me too. All right, E. Now, one way of looking at this might lead you to believe that there's two different inside functions, right? Because cotangent is inside the square root, but cosecant is inside the square. However, a little knowledge about derivatives makes this more clear. What should my u be? Cosecant or cotangent? If I make u equal to cosecant, what's du? What's the derivative? Cosecant, cotangent, negative.
No, that's not it.
So this cosecant, cotangent doesn't match up with my leftover here, right? So this is a good try, but not what I want. So what should I try after that? Try cotangent. If u is cotangent x, then du dx, the derivative of cotangent is negative cosecant squared. Ooh, I like that. Right, because I got a cosecant squared in there. That's pleasing. So du equals negative cosecant squared x dx. So the only problem, minor problem, is the negative sign. You can fix that up by putting a negative out front here. And then also putting one outside the integral. Balance it out. So here's your du. We didn't like this one. This one's wrong. So we had u equal cotan x, which means this is root u here. So altogether, when I change my integral, negative integral root u d. And we know to integrate square roots, we like 1/2 powers a little better. And then we know we should add 1 to the power, right? We use our power rule. Constant. Flip it up. 2/3 u to the 3/2 with a negative out front. Circle it, we're done. No, but I guarantee some of you are going to on the test. We'll see. Always got to get back to the variable you started with. Started with x's, so plug back in u equals cotan x. So if you guess the wrong u, okay, that's life. You have to notice that it's the wrong u and try something else. It'll happen. So, a couple more. One more trig and then a slightly different time. Set to go off in a moment. Sin x. So how do we want to do this integral?
That u equals sin x.
So if u is sine x, then the derivative of sine is cosine. But this x attached to the cosine is going to make that difficult because I'm not going to have any way to get rid of this x. I'll be able to get rid of the sines and the cosine, but not the x.
So let it equal cosine.
So if u equals cosine, then I can get rid of cosine, and then maybe du will be in my sines, but again,
Can you separate it?
okay, so one method would be to separate. Separation might work. All right, because I have a plus on top. So I can separate this into the integral sine x over x sine x squared plus x cos x over x sine x squared. Or the quotient of the x's. Now, what does this give me? So this guy here will be sine over sine squared gives you a single sine on the bottom. So this will be 1 over x squared sine x. Right, the x gets squared and the sine gets squared, but one of those cancels. plus, here the x gets squared, but one of the x's cancels. So it'll be cosine over x sine squared x. Have we made our life easier?
No.
I'm not sure either. I'm hesitant to say that this is any easier because just look, I don't know what to do with this first guy. I don't. Because this is a product and we don't have this is an x squared times a sine x and we don't have a product rule for integrals. And I can't do any u substitution on this first one because there's no derivative and there's no inside function in the derivative of the inside function. So maybe at some point in your life you'll be able to do these integrals, but right now we haven't made our life any easier. You need some sort of product rule to do each of these. So
Maybe the bottom up.
So maybe go back up to the original and try something else.
Okay, sounds good.
What if you did, wouldn't it be like x sine x?
Yeah, so being this is the u substitution section, try to find me a u here. This is outside, this is inside. That's one guess. So I might guess u equals x sine x. And then check it. What happens if you do the derivative? What's the derivative of this? How do you do it?
Do a product,
Product rule. You have to do product rule. So what happens when you do the product rule here?
sine x,
Derivative of x is 1 times sine x plus
Close.
x stays the same. Derivative of sine x is cos x. Oh. Oh, I like that. Sine x plus x cos x. Ooh. So this substitution will work. It's not obvious anyway. But it'll work. So du is equal to this whole thing times dx, which is exactly what I have right here. This whole thing times dx, that's my du. And on the bottom I just have u squared. So applying this substitution, my integral becomes the integral of du over u squared. I don't even have to multiply in any constants to fix this up. Right? I have exactly du right now. So you change it to u to the negative 2 du. Add 1 to the power. U to the negative 1 over negative 1 plus a constant. So negative 1 over u plus a constant. Flip it back down. And then put your x's back in. Negative 1 over x sine x. Sometimes you just gotta guess. Hope that it works out. Say that the math gods favor you. You made your daily sacrifice.
g, 1g.
Yeah, definitely G. We got some G action going. Alright, so this is a slightly different kind of, I mean, it's still an integral. You still use u substitution, but it's just a little different. So I can't do any algebra on this right now. Okay? If it were root x and then x plus 1, if it were like this, what can I do here? Now you can distribute. This is x to the 1/2 power, and it'll add to both. Okay? But over here, the x plus 1 is trapped inside the root. I can't do any algebra. I do have an inside and an outside function. My inside function is x plus 1, and my outside function is the square root. But if I let u equal x plus 1, du dx, the derivative is just what? 1. Derivative of x is 1. Which means that du is just equal to dx. So with this substitution, I have u right here, and I have du right here, but I haven't accounted for this x. And there's not really another substitution I can make. There's nothing else I'm going to make u that's going to simplify this. So is there any way that I can somehow account for this x using this substitution?
Multiply dx by
Multiply dx.
Is
So
that
dx is
equal?
du. You don't ever really want to mess with this.
Dividing x by
over
x.
x.
But this you can mess with. If u is equal to x plus 1, what's x equal to? U minus 1. Right? You can solve this for x. Right? The substitution, if u is equal to x plus 1, that allows us to say x has to be u minus 1. So what that will do is allow me to put in here
U minus 1.
u minus 1. And this is going to allow me to break the integral open a little bit. Right, watch. So the x becomes u minus 1. The x plus 1 becomes u. And then dx becomes du. I know it doesn't look like we've done much. But now that the binomial, now that the u minus 1 doesn't have a power, I can distribute. Right? I'll think of this as u minus 1, u to the 1/2, and then distribute into the parentheses. U to the 1 times u to the 1/2 is u to the 3 halves, you add the exponents. 1 times u to the 1/2 is just u to the 1/2. Now that I've managed to undo these parentheses and I have a minus in the middle, I can take the integral of each term separately. I can do u to the 3 halves, which I add 1 to the power and divide. And then u to the 1/2, I'll add 1 to the power and divide.
Do you divide that first one by 5 halves?
Yeah, I have to divide by 5 halves. My brain's getting ahead of me. Thank you. Yeah, so when you add 1 to 3 halves, you get 5 halves, and you divide by the exact same thing. And the next step, you can come up here and flip it, make it look a little prettier. And always put back in your x's or whatever variable you started with. So u is x plus 1, which means this will be 2/5 x plus 1 to the 5 halves minus 2/3 x plus 1 to the 3 halves. Boom. Shattered your reality. So how are you going to learn to recognize this trick? This is people. Like the tell, what you're really looking for here is a root x next to an x. And so if you have root x plus something, next to an x, even if this was x minus 1 or something, you might be able to use it, this trick. Right? This isn't usual U substitution because usually in U substitution you don't solve for the x. So this is kind of like an advanced application of U substitution. Well, let me give you a similar one so you can kind of catch on the pattern here. Integral of 2x plus 1 over root x plus 4 dx. I would hope, that I can make u equal to x plus 4 because it looks like x plus 4 is inside of the square root. So it looks like x plus 4 is my inside function. So you can try that. That makes du dx equal to 1 again. So du just equals dx. So we're in the situation where, again, the dx is accounted for, and the square root is accounted for, because this is just root u. But we haven't done anything with the 2x plus 1. So what do you think we can do with that? Solve for x again. Yeah, x is equal to what? U minus 4. So then I can plug in for x here, and the constants I don't even have to worry about, they'll take care of themselves. So I can change this to the integral of 2, but then instead of x, I'm going to write u minus 4 plus 1. All of this is over root u, and then dx becomes du. And when this looks uglier, it is actually better, because I can divide this root u into everything and simplify my integral a lot. So let's do some algebra first. On top, I'll go ahead and expand out the 2, I guess. 2u, so we'll get minus 8 when we multiply by negative 2, but then we add 1, and we'll end up with minus 7 altogether. So on top, I get 2u minus 7. Bottom, I get u to the 1/2. Split this up. U to the 1 over u to the 1/2 becomes, what's this simplify to? You subtract the powers when you divide, right? So u to the 1 minus 1/2. Minus 7u to the negative 1/2. Right, this guy pops up as a negative. And then each of those I can integrate using my power rule. Clean it up a little bit. Right, so I added 1 to the power, 1/2 became 3/2, then I divided by it. Added 1 to the power, negative 1/2 became positive 1/2 divided by it. Now I'm going to clean it up by flipping. 2 times 2/3, 4/3 u to the 3/2, minus 7 times 1/2, or times 2, I guess, when you flip it up. 14 e to the 1/2. Should you use back in, or your x's back in, I should say? Okay. Easy. Guys are you substitution masters? Yes. Yes? You're not going to disappoint me in your Calc 2 class? I'm not going to hear from your teacher. Josh, you gave me garbage. Let me hear, Josh, you gave me the best Calc 2 students ever. Seriously though, you kind of need to be able to do this really quick in Calc 2, so practice a lot. I'm going to do some definite integrals, and we'll certainly do lots of use substitution throughout the rest of the semester, but this will be pretty much the end of the section. And we won't do it again until we get to logs and exponentials. But I do want to do definite integrals. There's a slight problem with the limits, okay? So evaluate each definite interval. So I'll start with hopefully a straightforward one. The integral from 0 to root 5 of x root 9 minus x squared dx. I want to do this 2 different ways. And I'll let you choose the method that you want to use. So, one way to do this, remember the overall strategy for definite integrals now is to find the indefinite integral and then plug these in and subtract. Right? That was our first fundamental theorem. To do a definite integral, you can do the indefinite integral and then just subtract the limits. So I'm going to have to first do an indefinite integral here. How do I do the indefinite integral? If I ignore the limits, how do I do this integral? U sub. What's my u?
9 minus x squared.
9 minus x squared. Why?
Because x is the derivative.
Because if you do the derivative of 9 minus x squared, you get 2x, which is basically x, or negative 2. So the u here is going to be 9 minus x squared. So the du dx is equal to negative 2x, or du is equal to negative 2x dx. Which means in order to make everything work out, you need to put a negative 2 here, and then a negative 1/2 out front to balance it. Because then you have your u inside here, you have your du right here, negative 2x dx. So this will become the integral of root u du. Now I haven't put any limits. One method to do the definite integral is to keep the limits as x's and just don't evaluate them until you change back to x's. So to help me remember these are x limits, I'm just going to write x equals here. So I can't plug these in until I get back to x limits, or I mean x's in my integral. So I convert to u's, but I leave my limits as x's until I go back. Now, how do I actually do the integral of root u? Change it to u to the 1/2. add 1 to the power. Oh, I draw my constant. Don't allow me to draw my constant. It's a grave error. This guy was out front. Now, I need to evaluate this integral from x equals 0 to x equals root 5, but before I can do that, I have to get back to x's. So this will be negative 1/2 times 2/3 u to the 3/2 from x equals 0 to x equals root 5. Now I put my x's back in. What was u? 9 minus x squared. Now that I have x's, I can plug in my limits and be done with this. In fact, when you're plugging in limits, these constant multiples can be pulled out. Right? So let me pull out a negative 2/6 if I multiply those, which reduces, but let me pull that out so I don't have to worry about it. I just don't want to have to keep writing those over and over, so I pull them out front. Now I plug in root 5. So this will end up being 9 minus root 5 squared to the 3/2. When I plug in my top limit, minus 9 minus 0 squared to the 3/2 when I plug in my bottom limit. What's root 5 squared? 5. 9 minus 5? 4. 4 to the 3/2?
8. Oh, yeah, 8.
It's 8. Right? 4 to the 3/2 means do the square root and then cube it. Square root of 4 is 2. 2 cubed is 8. Okay. 9 minus 0 squared is 9. 9 to the 3/2, do the square root and then cube it.
27.
So the square root of 9 is 3, cubed is 27. So 8 minus 27 times negative a third. In some sense, this is much longer, not much longer. This is a little bit longer than it needs to be. But this is a perfectly legit method to evaluate definite integrals if you have to do u substitution. Basically, don't plug your limits in until you get back to x's. It's very common sense. Because you started with x limits, so you need x's before you plug in your limits. Questions? So the u substitution was exactly the same as before. Everything was exactly the same, except we had limits and we plugged them in after we got back to x. Now the other way to do this, which cuts out a little bit of the middle work, is to actually convert your limits from x limits to u limits. So I don't know which way you do. Sometimes one of them is easier than another. Sometimes one method clicks with someone's brain and the other one doesn't. It doesn't matter. But I'll show you the other method. So if you come back up here to the original integral, which was 0 to root 5 of x root 9 minus x squared, you can make a u substitution just like before. Du dx will be exactly the same. So du will be negative 2x dx. We have to do all the same stuff. We fix it up with a -2 out front, and then a -1/2. But now, I'm going to do one extra calculation right now. Well, two extra calculations. I am going to convert my x limits to u limits. All right, so I'm going to take this x equals 0 right here and convert it using this equation. If x equals 0, what does u have to equal? 9, right? Because you plug in 0. And if x equals √5, put the √5 here. Yeah, 9 minus 5 will be 4. So then you can get rid of the x limits and change it to u limits. So what my integral will have the -1/2 out front, but instead of going from 0 to √5, what will it go from?
4 to 9.
Should I do 9 to 4 or 4 to 9? 9 to 4. Right, the 0 corresponded to 9, so I should put 9 on the bottom. And the 5, the √5 corresponded to u equals 4, so I should do it like this. And then inside the integral, I have √u du. Here's my du, here's my √u. And I can do this, -1/2, u to the 1/2, from 9 to 4. -1/2, u to the 3/2 over 3/2. Evaluated from 9 to 4. Flip the 3/2 up, all the same now. But at this point, I don't need to go back to x's, I can just plug in my limits. So I'll have -1/3, I'll put 4 in, so 4 to the 3/2, then I'll put 9 in, 9 to the 3/2. So 8 minus 27. Oops. 6 of 1/2 doesn't make it.
That seems to kind of skip a step, make it an easier step earlier. Does it depend on the problem at that point?
I don't know. I have no idea. I always do it this way. Just because, I don't know. I never trained my brain to do this. But, whatever. The important thing is that if you do decide to do it this way, don't plug x's into u's. Right? If you plug x's into u's, you're wrong. Minus 1,000, you die. End of life. Game over. So if you keep your limits as x limits, go back to x's. If you change your limits to u limits, do it from the very beginning, and then you can plug them to u's. I'm bored with that. That's boring to me. Questions about u substitution? Definite integrals are very boring. I mean, they're cool. I like them. I like to be able to find the area, but it's a lot. It's a lot of tedious work. Yes, sir.
So we have the du up front when you're doing all this u substitution.
Yeah.
You take the integral, the du actually disappears because.
Yes. Yes.
Longer than 10 minutes?
So,
Because you're taking the antiderivative of the derivative, so it just kind of disappears.
yeah,
5 or 10 minutes? If you don't know how.
there's kind of two different ways to think about it. One way is that if you're thinking about this integral in terms of area, then the dx is your infinitesimally small width. So it's actually getting multiplied and added up and giving you a number in the end that's going on. Okay? If you're thinking about it in terms of indefinite integrals, so not area, just like this, the u is part of the the du is part of the notation for integral.
Okay.
Just like when we do du dx, the dx is part of the notation. It's telling you what to take the derivative with respect to. So yes, the d whatever does go away when you actually take the integral. This whole, both of these will go away when you take the integral.
It just kind of confused me because we were actually solving for d.
What? Say it again.
Multiplying the dx.
When we do like let u equal
Yeah.
whatever x squared plus 5 and then du dx is equal to 2x. Yeah, at this point we're treating the dx like that, like this guy, that infinitesimally small change in x. So it is itself a quantity like a number, and it can be multiplied up. So we're treating this like a fraction, which it is, right? Because the definition of derivative is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So we're basically multiplying this up with we're distributing the limit kind of, and then multiplying the limit of the delta x up on the other side. It's kind of fishy. I hear what you're saying. It's a little suspect,
I'll take your word for it.
but it works out okay.